7:20. Okay, so class has started, guys. Welcome. It looks like we're missing quite a few people, but I'm sure they'll be stumbling in late. Hope you guys are doing well. Hope the homework assignments are going well. Remember, if you guys ever have any questions with the homework, to email me or come to my office hours. Some of you have been coming to my office hours. That's just been great. We've been able to get a lot of work done together, and hopefully feeling really confident. So I appreciate those of you that have been coming to my office hours. It's just been a great opportunity to get everything done. Okay. And yeah, I did do a little trick with the title of today's lesson, but everybody caught that. All right, guys. So we're in 4.7 if you guys are following along in the book. Last time we did tangents, right? So we kind of closed up sine, cosine, tangent, and all that stuff. Oh my gosh, here comes everybody. So what we're going to do today is talk about inverses and what they are. So just I just want to do a couple of general things with inverses before we do in. So we're going to start with a little bit of review. So for example, if I had, my pen here, y equals x squared, right? The inverse of this, we would write, so our function, our output is y, and we do a little like this. Now, I know your books, if you read in books, it looks like it's y to the -1, but it's not a -1. The reason why it looks like a -1 in your book is that printing presses have limitations on what they can print. It would be much better if you put the negative down a little bit lower. I've seen some books do that as a trick, just to remind yourself that we're not saying y to the -1. That's a reciprocal, right? Reciprocal means 1 over. So when I do an inverse like this, right, this would be the plus or minus the square root of x. Okay, now this isn't a function, so technically I'm breaking the book's rule because they define an inverse as being anything that's a function, but I'm going to let it pass now because I'm better than the book. So not to be too cocky there. All right, so inverses, right? So inverses, this is one inverse that you're familiar with. Again, with the notation, it's not -1. That would be a reciprocal identity. This is an inverse. And so I've seen some books put just the negative down on the bottom, so it looks more like a backwards L. You can do it that way. Okay. So another thing I want to talk about is we've seen inverse before. Geometrically, right? So if I have a function, okay, so let's just stick with this, right? So let's say I have x squared, or something that looks like x squared. Then what an inverse is geometrically is let's see if I can draw this. What an inverse is a reflection over y equals x. And this is a really good tie-in to what we're doing today, is think about y equals x. Y equals x literally means the y and the x are switching places. Okay, so whatever your x's were, now they're your y's, and whatever your y's were, now they're your x's. And if you think of it that way, that helps really build an understanding for what inverses are. So what would be happening, I wish I had another color. What would be happening here is, then we're gonna have something like this. And of course I didn't draw oh my gosh, craft. Here, it should have gone over a little bit, so it should look something like that, and like this. Oh my gosh. Just forget it even happened. I'm so embarrassed. Okay, so again, in blue here, right, do you see how it's not a function, right? We have a positive and we have a negative, right? So the negative would be the one on the bottom and the positive would be the one on the top. Okay, now the book defines inverses as being functions, and we'll talk about that a little bit more. But the big takeaway here is geometrically, inverses are a reflection over y equals x. So that's really important to think about as we're doing trig, because the input and the output, right? Input, output, they're going to be switching, and it's really important that we think about that. So I just wanted to start with this, just a little quick review of things, right? Of notation and what an inverse is. How are we doing so far, guys? Sorry, I went a little quickly because I got super excited. I love trig. But does anybody have questions about this? That an inverse graphically is a reflection over y equals x, and that the inverse notation, what it looks like. Are we doing okay with that? Thank you, guys. I appreciate you using chat to check in with me. You guys rock. And I appreciate all my homies with their cameras on. I just want to say what's up to all my homies. Hey, guys. Yeah, it's good to see your faces. let's see here. We're just moving along. So again, little review there. So now that we have that little review, let's talk about, okay, well then how the heck are we going to do this with sine or cosine? Well, it gets complicated. And the reason why it gets complicated is why this gets complicated. The book defines inverses as being functions. But if you take a look at this blue graph, that's not a function, right? So that's why we have to break it up in terms of plus and minus. There's two parts, right? Because plus or minus square root of x isn't a function. Whenever you have to say plus or minus, not a function. Okay, so normally what we do when we take the square root of x, we just define it as being the square root of x. So what we do is we do a restriction. We do a domain restriction, right? So if I did a domain restriction on x squared and I only looked at the positives, then the inverse is only positive, and then now it's a inverse function, right? So the inverse is now a function. So the book just decided to say all inverses are functions. But in reality, we like to say inverse function, right? Because you can have an inverse that's not a function, okay? So that's what's going to make today difficult, just giving you a little heads up. Because if we take a look at trig functions, okay, what am I doing first? Let's do sine first. Okay, so here's sine of x. So if I'm going to reflect this over the line y equals x, and you're not going to have to do that this year because we're all online, and right? What's going to happen is that my x-axis and my y-axis are going to flip. So instead of going a wave going out to the right, I'm now going to have a wave going up. But as you guys can imagine, if I have a wave going up, it's not going to pass the vertical line test. Well, here, I'll just go ahead and do it. Right? So if I have a wave going up, right, you can think, right? So we're just kind of, can you imagine if I take this piece of paper, I wish we were in person, and I'm folding it, right? Like I'm folding it like that, so it'd go like that. So if this is going up, then I would have, right, it would break the vertical line test. Okay, so there's the problem that we have. So to do that, what they do is they give domain restrictions, okay? So these domain restrictions are called, now this book doesn't, I feel so, I want to teach you guys the right thing, but we're so hampered by this book. These are called principal values, okay? You know, I said that, and then you know now I'm going to spell the wrong principal. Okay, so it's principal values, right? And it's not the PAL because the PAL is a principal, right? Principal. Oh my God, I'm gonna lose my mind, guys. I forgot how to spell principal. Yes, this is correct. Principal. Okay. Whew. You guys didn't cover me, but I got my own back. Okay, so principal values. Okay, so these are values. So these are numbers or are a domain that makes inverse trig functions functions. Okay, right? So the book does this automatically. Oh, I'm gonna have to close my thing here. It's getting a little too bright. But the book just defines all inverses as functions. But we have to realize that they're doing a little bit of sleight of hand. So what they're doing is they're fixing the domain to make it so that the inverses are functions. Okay. So the principal values are going to be different for each one. So do I want to draw this by hand? Gosh, that's a really great question. So the key here is if we take a look at a unit circle, we want to be able to get all of the possible outputs without repeating. So for example, if I'm looking at, let's go red. If I'm looking at sine of x, I want all the possible outputs. So what are the possible outputs? Well, it's between 1 and -1 on a unit circle. Okay, so for me, all the possible outputs are between here. Okay, but I don't want repeats. So as it is now, right, I get my positive outputs to 1, but then I'm repeating over here, and then I get my negative ones, but then I'm repeating over here. So I don't want any repeats, all right, or else it won't be a function. So what they do for sine is they go from negative pi over 2 to pi over 2. So the principal values, I'm going to call them PV, they go from negative pi over 2 to pi over 2. Right, and I'm using the brackets to say that it can include those numbers. Okay. How are we doing so far? We're doing okay, guys? I'm not gonna lie. This is the most excited I'm gonna be all day about math. All right, here we go. Okay, so then if I take a look at cosine of x, okay, so look, cosine of x can go from +1 to -1. Okay, so then if I'm looking at here, I'm gonna go like this. Cosine, right? So we have this range, but I don't want to overlap. So if I start at 0 and I go like this, okay, I'm going 1 to 0 and then to -1. But as soon as I go down here, I start repeating. So I'm going to go from 0 to pi. So the principal values for cosine of x is 0 to pi. I should probably look that I'm not lying to. Yeah, I'm not lying to. That's good. Woo! Woo, woo, woo. Okay. All right. And then the last one, it gets a little bit trickier. But we talk about tangent. The only thing that we need to worry about with tangent, so I'm going to have a little separate space here. We might go off on a tangent. Yuck, 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 yuck. Remember with tangents, right, if we had a graph of tangent, the only thing that breaks down in tangent is the asymptotes, right? So we have tangent here. Okay, so for tangent, the principal values are just, you can't have your asymptotes. So actually tangent is the easiest kind of, at least for me, to remember of those two. It can't be the asymptotes. Okay, so those are your principal values. Okay, those are your principal values. So again, the principal values, we're just picking values that are representative of the whole function. That is, it includes all of the possible outputs, but doesn't repeat. And then the reason why we don't want repeats or anything is so that we can make sure it's a function. Okay? And so to show you that, so this is what we end up getting. So let's make a little table because this is what's important. Okay. So if we take a look at sine of x, the domain for sine of x is going to be negative pi over 2 to pi over 2. The range for sine of x is going to be -1 to 1. Okay, like that. So then if I wanted to take a look at sine inverse of x, okay, then we have to remember what is a inverse. It's a reflection over y equals x. Well, remember, domain is kind of like what works for your x. Right? And then the range is what works for your output. So if this is reflected over y equals x, then these are just going to switch. Okay, your domain and your range are going to switch. So here, my new domain is going to be my old range, and my new range is going to be my old domain. Okay, so they switch. And then you can say the same thing with cosine of x. Okay, cosine of x, the domain was going to be from 0 to pi. And then my range was going to be from -1 to 1. So then cosine inverse of x is going to be, my old range becomes my new domain. Okay. And my old domain becomes my new range. And vice versa. Oh, I got to do tangent, don't I? Okay. So tangent of, just tangent of x. The domain is, right, and these are principal values. So what's nice about principal values is that sine and tangent have the same initial domain. The range, right, if we take a look at the range of tangent, tangent goes to -infinity to +infinity. So we're going to have -infinity to +infinity. We can't use brackets there, right? Because infinity is a concept, not a number. So you can't equal infinity because it's just a concept. And then our new one, I'll go back to blue here. Our new domain is our old range. And our new range is our old domain. Oops, brackets. Okay, so you guys have that all in one place. So remember, to get from a function to this, you're just switching the domain and range. Okay, was that worth all that time? I hope so. Now, I'm not going to focus too much on graphing inverses just because we're online and graphing is kind of silly because you guys can just use Desmos to graph things. Does that make sense? So, but I do want to show you the domain and range restrictions, okay? So you can totally graph these on Desmos graphing calculator. I'm not going to spend a lot of time on that. If we were in person during a normal school year, we would spend a lot of time on just being able to quickly sketch these, okay? But because we're not in person, we're not going to practice sketching these. Okay. So what we are going to focus on, so you're like, okay, what are we going to do then? What we are going to focus on is what the heck do we do with these algebraically, okay? And how do we use the unit circle to help us out, okay? Because that's really important, and it's used quite a bit in AP Calculus, okay? Which quite a few of you guys are going to be taking next year. Or if you're taking calculus at the college, eventually, then that's going to be super important as well. Okay, just a quick check-in. Am I going too fast? Oh, I do get excited about this stuff. Okay, let's talk then. So guys, so we're not going to be graphing these, we're not going to be sketching these by hand. You guys can use Desmos graphing calculator to do that. But what we are going to be doing is we're going to be solving these algebraically. So again, we need to look at this. If I say I have sine, my input is an angle, and my output is a ratio. Okay, so again, I really want people to really focus on this. My input is an angle. Okay, my output is a ratio. Okay, so we have an input of an angle, an output of a ratio. Okay, really important that you guys know that, because as soon as I go to sine inverse, okay, things change. Now remember, an inverse means I'm switching my input and my output. This is like the theme, right? So the idea of reflecting over y equals x. My input is now my output is now my input. So I can write this in red. So whenever you have a sine inverse, your input is going to be a ratio, and your output is going to be an angle. So when we do inverses, we're always going to be having an input that is a ratio, and we're going to be getting out an angle, which is always so confusing when you use degrees, because degrees are totally made up and meaningless, right? But if we use radians, then this is really powerful, and this has a lot of meaning, right? Okay. Now, if you keep looking at this and you keep thinking like, crap, that looks like a -1, right? This looks like 1 over sine, but remember that would be cosecant, right? So remember, this is not a -1. This is an inverse symbol, okay? So do you guys see how that might be confusing? Because if this was a -1, that would be cosecant, okay? But it's not cosecant. So if you're having issues with that, you're not the only one, okay? People have had it, right? This has been around for a long time. So one way to get around that, instead of writing, oh my gosh, I always write written has 2 T's. Writing has 1 T. Oh guys, today's a bad day. Yeah, 1 T. Whew. Instead of writing sine inverse, okay, write arc sine. Now, the book doesn't teach it like this, but the capital A means you're using principal values, okay? And I don't think the book does that. The book just always assumes you're using principal values, so I kind of hate this book. But if you're not assuming you're using principal values, you make it a capital A, and it's just really easy to tell that you're using principal values, okay? So we have arc sine, okay? And I'm just going to write that down. Capital means principal values. Okay, capital means principal values. So instead of writing sine and then to the -1st power, you can just write arc sine. Arc means the same thing. So, and you can do this with anything. So there's arc sine, there's arc cosine. That's a little confusing with the double C. Arc tangent, etc. Okay, so the arc means inverse. Okay, arc means inverse. Okay, arc means inverse. So you're going to see that in your homework tonight. You're going to see that me using it in my notes. Arc means inverse. All right. Holy moly. All these notes, right? Let's just do some math, right? So what are we going to do with this? We're not going to be sketching it because we're all online and Desmos does that. But what we are going to do is we're going to be evaluating using the unit circle. Okay. So let's do an example of evaluating. Okay, so here's example numero uno. We're going to find the exact value. Now, when I say exact value, I mean don't use your calculator, don't use photomath, okay? It means I want you to use the unit circle. Now, I'm aware some questions photomath will do, but just remember, guys, when I'm making the midterm with Mr. Race and Miss Morris, okay, that we all know how photomath works, and we're going to give you questions that photomath won't work. Okay, just giving you guys a heads up there. So find the exact value. Okay, so the first one we're going to do, let's do arc cosine of root 2 over 2. And I'm going to be using principal values. And again, I hate your book it just assumes principal values. So again, I just want you to let guys know the book just assumes principal values because that's how they define inverse in your book. Okay. All right. So how do we do this? Well, remember, and this is why I made a big stink out of it. This is a ratio. Our answer is going to be an angle. So you can think of this as like, this is the ratio. What angle on my principal values gives me that angle? So first thing we have to remember for cosine, principal values are between 0 and pi. Okay. So then we have to think root 2. Well, I know that x is root 2 over 2 at pi over 4. And that's what it is. Okay? So what does this equal? This equals pi over 4. Okay, I don't want a decimal answer. I don't want you typing this into your calculator. I want you using the unit circle, right? So if we remember right, that's the coordinate point for that, and it's cosine, so we want the x, right? We want the x right there. So I'm just going to stop there for a second. You guys, are we cool with this? Now, remember, it's also online. So if you guys totally, I mean, you do want to have the unit circle quick access in your head, but if you don't, heck, there's Google, right? And if I can tell you, I have the unit circle just absolutely down because I teach it every year. But you guys want to get there eventually, but if you don't, there's always resources. What a time to be alive, right? Okay, let's try a different one. So let's say I try arctan. Oops, that's weird. It's like I can't even spell arc. Arctan of 0. I'm gonna have you guys try that out. Give it a second. Here. I'm gonna give you guys not a lot of time because we have a lot of things that we need to go over. Just take a second. Arctan of 0. Let's figure out if you can do that with the unit circle. All right, were some of you guys able to get that in that short of time? I'm testing your ability to do unit circles, right? Well, if you were stuck, I just kind of showed you what my brain did. I was like, okay, I know arctan, right? The principal values are from negative pi over 2 to pi over 2. I do know tangent equals sine over cosine. So the only way my ratio could be 0 if its sine is 0, right? Because if cosine was 0, I can't divide by 0. That would be undefined. So at the top and bottom here, those are my asymptotes, right? So if I'm looking here, then it looks like the only place where sine equals 0 is here, and that's at 0. Now, it's weird because this is a ratio. This is an angle. Okay? So it can get a little confusing when we're dealing with radians in that sense because, for example, with 0, are we talking about a ratio or an angle, right? If it was degrees, then we'd know to put a little degree symbol right here, and we would know, oh, hey, that's 0 degrees. Oh my gosh, are you guys having as much fun as I am? I'm mostly having fun because it's sunny outside and it's like beating on my face and I'm getting vitamin D. Maybe I should put on sunscreen. All right. Okay, so that's one thing that you're going to be asked to do not only in your homework, but on the midterm. Okay. Let's do some more. How are we doing for time? Oh, we're doing great. We're doing lovely for time. Whew, yeah. Oh, yeah. Okay. I don't want to do that because that's stupid. All right. All right. So the next thing is probably the most useful. So going into calculus, what makes calculus hard isn't calculus. There's only really 3 subjects in calculus, new topics. The rest of it is just like, oh man, I have to remember all of my algebra, right? So pre-calc is really good because it refreshes our algebra skills, right? But in reality is, in a year, you're probably gonna be a little rusty with your unit circle. So another way to do this is that we can use right triangle trigonometry to really help us understand what's going on with trigonometry, okay, with inverses and so on. So the next example or 2 that I'm going to do isn't like, hey, you're going to be doing this in calculus, but you're going to be doing something just like this. And it's really helpful when you're dealing with inverse trigonometric functions in calculus because you're going to forget some things. And right triangles are really easy. Okay, so let me show you what I mean. So again, this isn't exactly what you're going to be doing in calculus, but it helps set it up. If you guys want to, there's problems, example 7 in the book really sets you up for calculus, but we're not going to do that. Anyways, so what we're going to do is how to use right triangles. Right triangles to help with inverse trig. Sorry, I'm using shorthand because I was going to run off the screen there. Okay, so not invisible trig, inverse trig. Okay, so how to use right triangles to help with inverse trig. And what we're going to do here, so for example, let's say I want to evaluate tangent of arc cosine of 2/3. Okay, now the book calls this composite functions. Remember, composite just means 2 or more. So this is 2 or more trig functions. Okay, so and it's composite because it's one of another. But really, I don't really care about composites. You guys can do composites. You guys can do functions of functions. What I really care about here is how the heck do we make meaning of this? And especially as you go further in math, things become more abstract and more abstract and more abstract, and we got to have ways and tricks to make them concrete so that we can visualize them. Okay. Unless, I mean, you get to a certain point where concrete goes out the window, right? If you get to string theory, then no one understands string theory, so I guess you're okay. All right. So arc cosine. So what you're going to do is you're going to draw a right triangle. You're just going to draw a right triangle. And we're going to use right triangle trig. Now, you don't have to draw your right triangle like mine. However you draw your right triangle, be consistent. Okay? Always draw your right triangle the same way. Because remember, we don't want this to take a lot of time. This is just a quick sketch. Oh, crap, I can't remember my inverse on my unit circle. Okay, so this is just, you do a quick sketch. And this is what we're going to do. So arc cosine. So we have to remember that this is a ratio. Ooh, I just said ration. This is a ratio. And then you also have to remember SOHCAHTOA. Okay, not SOHCAHTOA, because that's weird. Okay, and it makes me a little uncomfortable to talk about that at school. But SOHCAHTOA. SOHCAHTOA. So if I'm looking at cosine, cosine is adjacent over hypotenuse. So what I'm going to do here is I'm going to plop down a reference angle. Let's say I call it theta. And then I'm going to say, okay, if this is my reference angle, cosine is adjacent over hypotenuse. So that means that this would be, my adjacent would be 2, my hypotenuse would be 3. Okay. So, check this out. Theta would equal arc cosine of 2/3. You guys with me on this? You guys, right? Here, do I need to go one step back? Here, I'll go one step back. Cosine of theta equals 2/3. So then if I take arc cosine of both sides, I get arc cosine of 2/3 equals theta. Now, why is that cool? We have to remember that this right here is theta. This is, so what are we really solving for? And this is where the graphic really helps. What am I really solving for? I want to know what tangent of theta is. Okay, I'm going to pause there. You guys doing okay? Does that make sense? Because that's really, I don't want to just teach you a formula. Does that make sense what we're doing? Right? So we create the visual to see, oh, arc cosine of 2/3, that's really a right triangle with the reference angle with the adjacent being 2 and the hypotenuse being 3. Okay? And then that means that this is really an angle. Right? This is really an angle, so I'm really finding tangent of theta of this triangle. And I appreciate the people using chat to check in. I appreciate you guys. But I just want to make sure, remember guys, this isn't about me. I already know this stuff. I'm pretty good at this stuff. Maybe I could use a little tips for spelling, my little spelling errors. But how can I help you guys? We're doing okay? Sorry, I teach Algebra 1 Extended and then Geometry before this, so I always forget that sometimes I have students that get things really quickly. Are we all good though? Yeah. No, the visual is really baller. Okay, so now, if we're really looking for tangent of theta, right? Tangent is opposite. Well, I'm missing, do you guys see that? I'm missing my opposite. So we have to find this, to find tangent of theta, we need to figure out, right? We need to figure out this, because remember, tangent of of theta is going to equal a ratio. So to do this, what's the other thing, right? We have SOHCAHTOA, but the other one is Pythagorean theorem, right? So I would know that, I'm like switching up colors everywhere here. So I would know that 2 quantity squared plus star quantity squared equals 3 quantity squared. So I know that star equals, now it should be plus or minus, but we only want the positive, right? So then it's going to be 3 squared minus 2 squared. So I get star equals 3 squared is 9, 2 squared is 4, 9 minus 4. Oh, I'm going to have to use my digits. 9 minus 4. So that should be 5. And then, so it's the square root of 5. Oh man, we're doing some really heavy duty math here today. I had to bust out the old digits. Oh man. Mr. Schmetz here is probably thinking like, who is this guy? And how did he become a math teacher? Like, what? Okay, so now what's tangent, right? So again, what's tangent of theta? Oops, using all different colors here. What's tangent of theta? Tangent of theta is, so this side is root 5. So it is opposite, so root 5 over adjacent, 2. That's it, that's your answer. Sorry, that was kind of anticlimactic. I'm so sorry. That's your answer, yeah! There you go, that's more exciting, right? So that's what it is. Okay, so it looks like we have about 11 more minutes. We're gonna have to do a couple more of these to figure this out. Does anybody have questions before we do maybe, you guys want to try one out on your own? How confident are we feeling? I made it look more complicated than it is because I had all these extra notes. Do you guys want to try one on your own? Ooh, 10 out of 10 confident. You know, it was really funny. There was a study about math students, and they compared them to all the math students in the world. And there is one thing that American math students scored higher on than any other math student in the whole world. Do you know what it was? Confidence. American math students were always more confident in their math than students from other countries. Well, how about this? Let's do one more together, then I'll have you guys try one your own. Okay? So let's try one together. Okay. So let's say, so here's our next example. Our next example is cosine of arc sine of negative 3/5. Okay, and we're going to evaluate this. Okay, so to build up, because I got some messages that we weren't feeling too hot, so we're gonna go ahead and do this one together. Okay, so what am I gonna do? I'm gonna draw a triangle, and I always draw my triangles the same, so that way I'm not messing with my brain. Okay, if this is too easy, you could draw your triangles differently and mess with your brain. So sine, so this is arc sine. So if I call this my reference angle, I always put my reference angle in the bottom left, okay? Then sine, we have to remember sine is opposite over hypotenuse, okay? Now, I drew this wrong,
right? Okay. So if I were to draw this correctly, it would look like this, right? Because I have -3 and my hypotenuse is 5.
Do you guys see how that would be drawn correctly?
Okay, but remember, I'm not trying to draw a picture correctly. That's not my goal. My goal is to get the answer. So I always just draw my triangle the same. Just put a -3 there and know that this picture isn't correct. Remember, it's an aid. We're not being graded on, did you draw this triangle correctly? That will come later in this trimester when we do vectors. Okay, but we're not doing vectors now. This is just a helpful little piece, right? So it's okay if you just have a -3 here and it's still going up. You know it should be going down, right? Okay, and then the hypotenuse is 5. Now, I hope I didn't confuse anybody with that. Does this make sense? I have arc sine, so that means sine is opposite over hypotenuse, right? The negative will always go with the top number. Okay? So if it doesn't say, the negative goes with the top number. That's just a rule of thumb. Okay. How are we doing here? Do you guys see this? Okay, cool. All right. So then we want cosine. Well, cosine is adjacent, isn't it? So we don't know this one, right? So if we're going to get cosine of theta, right? Because remember, this equals theta. So we want cosine. This is really saying cosine of theta, right? Because the output of an inverse is an angle. And cosine of an angle equals a ratio. So we want the ratio of cosine of theta. So I want this. So I'm going to use Pythagorean theorem. So what do we want to call this? I liked it when we called it a star. Star squared plus, and this is why we always put parentheses, right? Right? Always use parentheses, equals quantity 5 squared. Okay? So if I solve this, then I'm going to have my star equals, we're only going to want the positive because we're talking about distance, 5 squared. And then when I square a negative, that's the same as squaring a positive. So I'm just going to say minus and then 3 quantities squared. Okay. How are we doing there? Is everybody doing okay? Maybe I'm going too fast. I sure do get excited about trig. And I want to hear from my students that weren't feeling too confident too, right? Make sure you guys, if you guys aren't feeling confident, you tell me where I'm losing you. So what is this? 25 minus 9. So this is going to be 14. Gosh, I almost wrote down 7. That would have been really silly of me. Square root of 14 isn't 7, right? Okay. Square root of 49 is 7. Okay. So then that's my answer. So cosine is adjacent over hypotenuse. My adjacent is square root of 14. My hypotenuse is 5. Right? So just remember, how am I getting this? We can think of this as cosine of theta equals, right? And so if this is the square root of 14, then my answer is square root of 14 over 5. Oh my God, it's 16. All right. I made a mistake. You guys are actually paying attention. Yeah, I want to say I did that on purpose, but I was just focusing on everything else. All right, that's cool. That's cool. I'm cool. Hey, there you go. Square root of 16. Easy fix.
Thank you for my 2 homies who are keeping me in check. I appreciate that. Oh man. See, even when you teach math, you make mistakes. I love it. That was a pretty silly mistake.
How come I didn't do a -3? Because think of it this way. We can go ahead and do the squared now. So the quantity of -3 squared is 9, and this is 25. So I'm going to go ahead and subtract 9 from both sides. So this would be, so if we follow the work, I would get star squared equals 25 minus 9, right? So that's why we put the parentheses around here, because a negative times a negative is a positive, right? So this will be positive. So negative 3 times negative 3 is a positive 9. So I'm subtracting 9 from both sides. And then I square root both sides. So I get the star equals the square root of 25 minus 9, which is the same as the square root of 5 squared minus 3 squared. Oh, yeah, square root of 16. 4 times 4 is 16, right? So then I would write my answer as this. And you might recognize this as a Pythagorean triple, right? 3, 4, 5. Okay. Yeah, you should. Sorry. I got all sorts of thrown off, and I'm trying to go through the comments now. Yeah, square root 16 is 4. 4 times 4 is 16. Yeah. You guys want to try one on your own? I think you guys should try one on your own. Let's try one on your own. Hopefully I didn't make any other more mistakes. So why don't you guys try this one on your own? Ooh, that's ugly. I don't want to do... Ooh, do you guys want to do a really ugly one, or do you want to do a nice one? What do you guys want to do? Vote on it. Ugly or nice? Okay, I'm going to do 2. So here's the nice one. So I'll let you guys choose your ability range. Okay, so if you want to do a nice one, do this one. If you want to do an ugly one, oops, oh my gosh, ugly. Oh my gosh, I can't even. The ugly one is this one. Tangent of arc cosine of 2x. Okay, so you guys pick. I'll go over it in a couple of minutes. Here, let's put a couple of minutes up. So you pick which one you want to do. You can do the ugly one. I even made it ugly. How fun is that? And then, or the nice one. All right, guys. With time limits, I'm going to go over both of these. So for the first one, for the nice one, okay, I am going to, it looks like it's cosine, right? So if I have my reference angle, I know cosine is adjacent over hypotenuse. So this is 2 and this is 3. So I'm going to go ahead and solve for that star because I'm going to need sine. And sine is opposite over hypotenuse. So I'm going to do star squared plus 2 squared equals 3 squared. And then that means the star equals the square root of 3 squared minus 2 squared. So what is this? 9 minus 4. So that's 5. Oh my gosh, crap. So this is going to be square root of 5. Right? Oh my gosh, did I get that right? Yes, I got that right. Okay, so this is square root of 5. So then sine of theta is going to be square root of 5 over 3.
And if you guys want me to go over that a little bit more in depth, stick around just a little bit. And I can do that because I want to respect your time and go over this one really quick. So I'm going to draw a right triangle. So cosine is 2x. So there's a couple different ways, but the easiest way to do this is to use a unit circle. So cosine is 2x over 1. I call this theta. And then I have to find the star. So star squared plus the quantity of 2x squared equals 1 squared. So that means that this equals the square root of 1 minus 4x squared. So this equals, right? So that's this right here. So then tangent equals opposite over adjacent. So then this is going to equal, let me get red here. This is going to equal the square root of 1 minus 4x squared over 2x. And I'm just going to leave it like that. And that's my answer. Okay, so thank you guys for today. I will see you guys Thursday. Take care. Enjoy the awesome weather. If you have quick questions, you can stick around. Come see me in my office hours or send me an email. Bye, everybody.